Hello everyone, welcome back with another lecture. And today we are going to discuss binary search from your SD sheet. So let's move to the problem. I hope you all can see my screen. Okay. From your SD sheet, you can access the problem right from here, binary search. So let's move to the problem. I think this is giving some issue as of now. This will be fixed. We can solve it from here. Okay. So binary search is one of the searching algorithms in arrays that we use. Now let's discuss about binary search. As the name suggests, it's a searching algorithms. The prerequisite that it takes to search is that in your array, the elements should be in the sorted order, right? This is one prerequisite. Other prerequisite is, if we think from the broader perspective, it is used to it can be easily used in algorithms of machine learning, right? Where it does some searching in such a way that it divides into two halves. Okay, neural networks, I guess. Then other thing which binary search helps is in the cloud where the data is stored. So it reduces the time complexity, and by how much it reduces, I will come on that point. The other condition that it takes in the real world scenario is that the data from which it is searching, that should be in the contiguous order. That means the order in which the array stores the element. And second thing, if we are talking about arrays, it should be in sorted order. Okay, so these are the prerequisites. Now coming on to binary search. Okay, so let's say that we have this array from which we want to search the elements. So we have 1, 2, 3, 4, and 5. As you see, this array is already in sorted order, right? And what you need to search is, you need to search an element 4. K is the element to be searched, n is the length of your array, and this is the array itself. Okay, so you want to search 4 in this array. Your K is 4. How will you search it? What does binary search do? So let's understand what does binary search do. So let me write it this way. Let's understand the algorithm of binary search. We have 1, 2, 3, 4, and 5. Okay, so if we were to search it linearly, in linear fashion, what comes to your mind? We can take a for loop, right, starting from 0 index till n minus 1th index, and keep a check if that ARR of I is equal to the element we are searching. We can simply return that index. In this problem, the problem statement says that you, given a sorted array, find the position at which k is present using binary search. So you have to use binary search to find that index if that element is present. So if 4 will be present, this I am telling you by linear search. Linear search, what happens in linear search? You simply check for each element, you check, and if you find the element, you will return that index itself. But you see that we are iterating over each element, right, in linear fashion. So we are checking for this, and whenever we find it, we are returning it. That is okay. But let's say in the worst case time complexity, if your element is present here, it is going to take n of time, and binary search is going to reduce this time. How? That we will understand. Okay, so let's apply binary search algorithm in this test case. So what it does is, binary search actually divides binary search divides your problem into half each time. So binary search does what? It divides the search into half. How? It divides the basically the elements, or that window into half. each time. By this, what do I mean? Have a look here. So if I check, I can keep two indices. One is low. Okay, let's take two indices. How do we divide into half? That is important to understand. Have a look here. So let's take two indices. One is low. Low index starts at index 0. That is the start of your array. Other index, we are actually keeping the track of that window. So initially your window is the entire array itself. So high will be the last index and low will be the this index. And then what you need is you need to find mid element. So mid index would be equal to low plus, this is how you can find the middle index, high minus low divided by 2. So if you do perform these operations, you can find the mid index. So if your low is 0, your low is 0, this is index 0, this is 1, this is 2, this is 3, this is 4. Low is 0, high is 4, 4 minus 0 divided by 2. So your index will come out to be 2. So right now you will see that your mid element is 2. Okay. Then you keep a check. If your middle element, check it, is your ARR of mid equal to the element that we want to find? Is it equal to k? If that is the case, you will simply return mid, right? What can be the other cases? Let me check if you can see my screen. Okay, fine. So the other cases can be if your ARR of mid, either it is less than or greater than, let's say it is less than k. So if ARR of mid is less than that given element, right, that means one thing is for sure, that your array is always in sorted order, right? You check for this element, your mid comes to be 2 in this first iteration. You check, you see that your k is 4 and ARR of mid is 3. So 4 is not equal to 3. And what is the status as of now? Status is that the index at which you are checking for the element, it is smaller than the element that we want to find. So our search should be in which window? Should our search be behind this index or after this index? Clearly, we know that your array is sorted. So with this information, we can easily know that if we go to the right of my mid index, if this is your mid index, let's say this is your mid index. If you go to the right of your mid index, you are always going to find elements greater than ARR of mid, right? And if you go to the left of your mid index, you are going to find elements that are smaller than ARR of mid, right? So elements are going to be smaller than ARR of mid elements. Now, the current element at which you are present, it is smaller than k. That means your search should be towards the right because you want a bigger element than ARR of mid. So ideally your search should now be, the window of search should be from mid plus 1 to last index to the remaining all the elements, that will be till n minus 1th index. So your low will become mid plus 1, your high will be this. Okay, if because your element, let's say it was what? Your k is 4, and that is I'm considering element to be ARR of mid. ARR of mid came out to be less than your k. That is why we are doing this operation. Understood? Okay. Now coming on to moving ahead. Now let's check what is your low and what is your high. So low becomes, L becomes what? What was your mid? Mid was 2. Low becomes 3 and high becomes 4. So the operations would be for like this. Your array now would be 4 comma 5. Okay. You calculate, this time your low is index 3, your high is index 4. Then you check what is the mid. Mid will be low plus high minus low divided by 2. So that will come out to be, oh, I say 1 by 2. What will be your, see, this will be low plus 4 h minus L divided by 2. Right? So 1 by 2 is what? 0. And 3 plus 0 would be what? 3. So your mid will be at position 3 only. So you do a check. If ARR of mid is equal to k, so this is index 3, this is index 4. Let me write it. So this is index 3, this is index 4. Now you check your ARR of mid. Is it equal to k? Yes, it is. So simply I will return 3 and your work will be done. Right? This is how you are doing it. Let me take one more example so that you can understand the problem even better. And let me keep this algorithm as it is. Okay. So basically, I'm putting a check. Now let's say your given array again is 1, 2, 3, 4, 5, 6. Right? And you need to find 6, let's say, or let's say 1. Find 1. If that is present, return the index. Okay. So first iteration, I'm writing the iterations here. In your first iteration, your low is initially 0. Your high is initially what? This is, let me write the indexing also. This is 0, 1, 2, 3, 4, and 5. So high is 5. Okay. So your mid in this case would be 0 plus 5 by 5 minus 0 by 2. So that will be 2. Right. So this is going to be your ARR of mid in the first iteration. Okay. So by when? How long are you going to keep a check for all these conditions? This check will be for while your low index is less than or equal to your high index. For those cases you are doing so. Okay, if ARR of mid is less than k, what are you doing? That means you need to find elements after mid. Your window will be from mid till high. So your low will become mid plus 1. Otherwise, in your else case, your high will become mid minus 1. So let's understand via this pseudocode what are we doing. Okay. If your k is greater, yeah. So have a look. In the first case, mid we calculated. We calculated mid. Then we check ARR of mid. ARR of mid is what? This is your ARR of mid. Now you will think this is even indexed array. This is even means this not indexed. This is an array which contains even number of elements, right? It contains total 6 elements. So in that case, 2 or 3 both can, one of these can consider as your mid. So the formula that we have used here is going to give you a lefter, means the first index that comes out of these two as your mid index. Fine. So right now we have ARR of 2. So compare ARR of 2, that is equal to 3. So 3 is greater than 1, the element that we want to find. In that case, if ARR of mid is greater than the element, this is ARR of mid, this is K. If it is greater, then what do we do? Our window becomes from this index, because our high becomes L mid minus 1 and mid is 2. So now your high will be, it will look something like this now. Now your comparison would be for these elements. Why? Because now in this case your L is 0 and high is 1. Because you did H is equal to mid minus 1. So you reduce the size of your window. Fine. Okay. Now let's do a check. What will be the mid in this case? Mid will be 0 plus 1 minus 0 by 2. So that will be 0, right? Now you check ARR of 0 is 1. 1 is equal to 1. So in this case, you are going to, when you do a check, you simply return 0. That is, you have found it. Let's say you wanted to find 6. Then what? Initially, your mid was what? 2. And you check that ARR of 2 is less than your k. When ARR of mid is less than k, your window becomes from mid plus 1, that is index 3. So index 3 we have 4. So the elements of comparisons would remain these elements in your array. Okay, this is not literally we are reducing the size of array, we are just reducing the size of a comparisons of the elements. Okay, now your low is at what index? 3, and your high is at index 5. What is the mid in this case? Mid in this case would be 3 plus 5 minus 3 divided by 2. So this will become 4, right? So now your comparison would be at this index. Check 5 with 6. 5 is less than 6. So when your mid is less than that given value, what do? Your window size becomes from mid plus 1 till high. So now your window becomes something from what is mid plus 1? Mid plus 1 is mid is fourth index. Now mid plus 1 will be fifth index, and high is also at that index only, that is index 5. So your comparison window would be of just one element, and low is also this element, high is also this index, low is also this index, high is also this index, so mid will also be this index only. And then you do comparison, you will find that ARR of mid is k, so you return the index of this element, so you return 5 in that case. I hope you have now understood this problem. Now coming on to the time complexity. So we see that at every step we are dividing the window of comparisons into half, right? If initially the length of my array was 6, then I divided into what? Length of 3, right? Whatever my comparison was, let's say on average we are taking, don't think that this is 3 minus 1 equal to 2. This is the reason that we already considered this, and then we are moving to this other remaining 2. If this was of length 7, then it will be equal 3 3, because already the mid one we have compared, so it is something that, so it becomes half the size of your array, right? When it was 3, right, when it was 3, you reduce the size to almost half of 3. So 3 by 2 in code, in programming, would be 1, so it reduced to 1. So on and so forth. Fine. Now this will be the end. Okay, how many steps it took? It took 2 steps of comparisons, this step and then this step from the original step. Let's understand it using an array. Let's say the length of your array was 8. If length of your array was 8, in how many steps our comparisons would have been done? So in this case, when you divide the array into half, 8 divided by 2 will be 4. Now 4 elements are there in your array which you want to compare. Now you will find the mid of these 4 elements, and then you divide the comparison, and the elements of comparison will be 4 by 2. So you will be comparing 2 elements right now. When you have 2 elements, you will be comparing 1 element each at a time. Okay, so in how many steps, your comparisons, all the comparisons that you were required to do in order to find error of mid happened? So total 3 comparisons. So do you see a pattern? Log n number of elements base 2 is the time complexity of binary search. You are searching an element in a sorted array in total log n of time, where 8 is n. So log 8 base 2 will be what? Nothing but 3, and that is the number of steps in which you are dividing, and that is less than, at any point in time, log n would be less than n, right? So I was telling you, log 8 base 2, it is what? It is equal to log 2 to the power 3. That is actually the number of steps we are using for a searching algorithm, right? So it will become equal to 3, because log 2 base 2 is 1. Understood this problem? So this is your binary search algorithm. If you check for this, let's say if we wanted to find what is the mid in this case, it is 1. That means this index 0. So in that case, your array, let's say we want to find 7. I want to find 7 in this array. So how will I make the comparisons? Last iteration that I want to do, means not iteration or the explanation. stepwise. I want to find element 7. So my comparisons would look like what? Now your low is 0, high is 1. What is your mid? Mid will be 0 plus 1 by 2, that is 0. So your comparison window would be 1 only. And I have not found here also. Okay. All anyway, when I knew that I want to find 7, I will never go at this position. I will always be searching it towards this, and I'll be at this window of my element, I'll check that still I have not found the value that I want to find, and my low will exceed the value of high. Because when I do low is equal to mid plus 1, mid in this case is what? Index 5, and 5 plus 1 would be 6. That will be index out of bounds. And I will exceed the index of high also in this case. So I will simply return minus 1. So you understand this thing how nicely, how with ease binary search with has taken the help of the information that your array is sorted, and with that information it is only searching in the window where it is possible to find. Why would I find in this window when there are no chances of finding 7? Because I have elements greater than 3 also, greater than 4 also, greater than 5 also. So it's when I divide it into half, I divide it in such a way that there are high probable chances of finding that element. So that's how it is reducing the time complexity as compared to linear search from n to log of. I hope this is clear. Okay, and आज के लिए we'll do just one question, which is every day we take up one question only, and we solve it from your SD sheet. Okay. Fine. So before we move to the code, there is also another way. I told you iterative way of using binary search. There is also recursive way of solving binary search, because we are at every step we are doing the same thing, right? So the recursive call can be made in this way. Let's say binary search, it takes your array int ARR, your low index, your high index, right? And then you check if your low index is less than or equal to your high index. Then you make your things. First thing is that you calculate some mid, int mid, let's say int mid is equal to what? Low plus h minus L divided by 2. Then you check if ARR of low, sorry, ARR of mid is equal to k. So we will also pass k in this recursive function. We will pass k. I'm just writing the pseudo code. Okay. So if that is equal to k, what are you going to return? Return mid. That is the index itself. Else, if ARR same conditions, just that we are going to call it recursively. If ARR of mid is greater than k, that means you should call a search, binary search, call return binary search function for values of low will be mid plus 1, because your mid is greater. If your mid is greater than k, that means you should find in the window from low to mid minus 1. So low will remain low. See, let's say your k is 5 and your mid is 7. So obviously your 7 would be somewhere here, and you'll get elements greater than 7, and here you'll get less than 7. And you want to find 5, so you will find 5 here or here. So obviously here. So your high index will become mid minus 1. I hope this is clear. So L will be passed as L, your high will be passed as mid minus 1, and the other parameters are same. Otherwise, in the else case, you don't even need to write else. You can simply write return. No, it should be else. Return binary search ARR. Now your window will be mid plus 1 till your high, and k will be passed as it is. So this is when this condition holds true. Otherwise, you return. That means you have not found any value equal to k. You return minus 1. So this is how we are calling them recursive. This is your recursive. That is about it. So I think we can move to the code now. We'll solve it iteratively. In both the cases, iterative or recursive, you know, recursion also goes and calls, it makes a recursive call. So log n is a time complexity it is going to take for all the recursive calls. That is about it. So moving to the code now. So let's code it iteratively. I'm going to do right now. I will be at n minus 1 while your low index is less than or equal to your high index. You are going to calculate mid. That will be equal to low plus, let me write it properly as, make it so that you can understand. Okay. Mid is equal to low plus high minus low divided by 2. That's your mid index. You check, is ARR of mid equal to the element that you want to find. If that is the case, return mid, the index itself. Else, if ARR of mid is less than k, that means k is greater. So your search window will be your mid low will be equal to mid plus 1, right? And otherwise, else your high will be equal to mid minus 1. That is what you're doing. If your ARR of mid, let's say this mid value, it is less than k is 4. So now you will be checking for this values, these elements. For these elements, I can put my low pointer at mid plus 1. That's what I have done, and high will remain at whatever position it was. In other case, let's say if my element was somewhere here, 1 which is less than ARR of mid, so my high pointer will become mid minus 1, low will stay where it was. This is what I have done here. And the iteration will keep on going until your low is less than your high index. They should not exceed each other, right? That's how we are doing. And then in the end, return minus 1 if you're not. Fine, that is about this problem. So I hope you have understood this. If you have any doubt, you can ask me. So let's wrap it up for today and see you all in tomorrow's lecture. We will be solving problems serial wise, which are present in your SDE sheet, which you can find here. These are the questions. I'll just show you. So these are the questions that we are going to take up now. Okay, fine then everyone. See you in the next lecture. Thank you. Bye bye.